Swayam Prabha. Digital India. Educated India.
Hello students, this is Professor Ravin Zugade from Department of Chemistry, Rashtrasanta Tukadoji Maharaj, Nagpur University. And in this particular course, we are discussing about the BSc first year semester 1 course on inorganic chemistry. And this module is based on the chemical bonding. We are discussing about various theories of chemical bonding in this particular module. This lecture has been prepared under the academic expertise of Professor L.J. Paliwal. The outline of this module is ionic bonding, covalent bonding, theories of covalent bonding, metallic bonding, and weak chemical forces. In this lecture, we will be discussing about the molecular orbital theory aspect of the covalent bonding. In the previous lecture, we have discussed about the molecular orbital concept and its application to the homonuclear diatomic molecules right from H2 to F2. Now we will be discussing about the molecular orbital theory aspect for the heteronuclear diatomic molecules in this lecture, followed by the VSEPR theory. Let us start with this lecture. The first heteronuclear diatomic molecule we are going to discuss here is the HF molecule. Now, since it is a heteronuclear diatomic molecule, the electronic configuration of hydrogen and fluorine are not identical, neither their energies are equal. If we consider the electronic configuration of hydrogen, it is 1s1, and fluorine, atomic number 9, has an electronic configuration of 1s2, 2s2, 2px1, 2py2, 2pz2, or you can have 2px2, 2py2 and 2pz1. So this single electron can be present in any of the three degenerate orbitals. Now, if we try to plot the energy level diagram according to MO theory, the electronic energy level of this 1s subshell is much higher as compared to 1s subshell of fluorine. Also, it is much higher as compared to the 2s energy of fluorine. So 1s cannot overlap with 1s or 2s orbitals of the fluorine atom. However, the 1s of hydrogen has a comparable energy as that of the 2p orbitals of the fluorine. So it can mix with any of the 2p orbitals. For example, if it mixes with 2px orbital of this fluorine atom, then what will happen? We will get two molecular orbitals, one with a lower energy called as the bonding molecular orbital, and second with the higher energy called as the anti-bonding molecular orbital. Now, since the bond between s and p orbitals is a sigma bond, this will be represented as sigma sp because it is formed by one s orbital and one p orbital. So sigma sp molecular orbital and sigma sp star or sigma sp asterisk, that is the anti-bonding molecular orbital. Now, in this case, the second shell of fluorine is the shell which is involved in bonding, but it has 2s, 2py and 2pz orbitals which do not find any orbital in hydrogen with which they can form bonds. So these three orbitals remain as non-bonding molecular orbitals with the same naming as a 2s, 2py and 2pz. So these are the non-bonding molecular orbitals. They retain their identity even in the molecular orbital form. Now this is atomic orbital of hydrogen, this is atomic orbital of fluorine, and these are the energies of the molecular orbitals in HF. Now there are 7 electrons in fluorine and 1 electron in hydrogen. So overall 8 electrons are to be filled, and they will be filled as 2s2, sigma sp2, 2py2 equal to 2pz2. So these two will be degenerate, whereas sigma sp star will remain vacant. So the electronic configuration of this molecule can be shown as HF. This is K. This is K of fluorine, followed by this 2s2 sigma sp2 and pi. This is 2py2 equal to pi. It is 2py2 equal to 2pz2. These two have equal energies, and we can calculate the bond order as number of electrons in bonding minus number of electrons in anti-bonding divided by 2. So number of electrons in bonding are only 2, number of electrons in anti-bonding are 0. So the bond order will be 2 minus 0 upon 2 will be equal to 1. Now it should be kept in mind that the non-bonding orbitals neither favor the bonding nor oppose the bonding, and so these electrons are not considered during calculation of the bond order. Coming to another molecule, which is a HCl molecule. Now in HCl molecule, the only difference is that instead of 2 or 2s, 2px, 2py and 2pz, we have 3s, 3px, 3py and 3pz. So the molecular orbital energy level diagram for HCl molecule will be exactly similar to HF. The only difference will be instead of second shell, we will have third shell, and the electronic configuration can be shown similar to the HF molecule with only third shell instead of the second shell. The bond order will be again 1, indicating that H and Cl are bonded by a single bond. Coming to CO molecule. Now this is an interesting molecule as far as the molecular orbital theory is concerned, because this is another limitation of the valence bond theory. Any theory which can explain CO molecule should explain 4 important properties of this carbon monoxide molecule. The first property is the bond order of CO is 3. That is, carbon and oxygen are bonded by a triple bond. Secondly, this molecule is non-polar in nature with the dipole moment of only 0.1 dBi, indicating that it is a non-polar molecule. Thirdly, this molecule has a tendency to form sigma bonds by a property called as sigma donor property. So it can form coordinate bonds through sigma bonding, and it has tendency to donate the lone pair of electrons for the bonding. And fourthly, this molecule has got a tendency to act as a pi acceptor. It has a tendency to accept electrons in the pi bonding or through pi bonding. So these are the 4 important properties of carbonyl molecule or carbon monoxide molecule, and any theory should be able to explain this theory. Now the electronic configuration of carbon and oxygen can be shown as this. So carbon has got 2 unpaired electrons in second shell, while oxygen also has got 2 unpaired electrons in the second shell. So if we consider the valence bond approach, both carbon and oxygen are capable of forming 2 bonds. So if they form 2 bonds by using their unpaired electrons, definitely the bond order will be equal to 2, and the molecule can be shown like this: C double bond O. Now if we look at these 2 properties, we can see that this molecule is definitely non-polar, explaining the negligible dipole moment or non-polar nature of this carbon oxygen bond. But it is contradictory to the bond order, which is an observed bond order of 3, whereas the bond order which is obtained from this particular configuration or this type of bonding will be equal to 2. So this is contradictory. It means that we cannot explain the bond order on the basis of this type of bonding. Okay, so now we can consider there is a third possibility, that this 2pz of carbon is empty and 2pz of oxygen is having a lone pair. So if they overlap sidewise, then they can form a pi bond, and if they form a pi bond, it can be shown as a coordinate type of bond, because oxygen is sparing its both the electrons for bonding, and if this type of bonding is there, the bond order will definitely come out to be equal to 3, which is matching with the observed bond order of 3. But at the same time, this oxygen and carbon will definitely get the charges because oxygen is pairing both of its electron for bonding, and so oxygen will acquire a positive charge and carbon will acquire a negative charge, and this will induce the polarity to the molecule. And since the molecule is becoming polar, it is contradicting the negligible dipole moment or non-polar nature of the molecule. So in short, we can say that we have got two aspects, the bond order 3 and negligible dipole moment. If we try to explain the non-polar nature of carbonyl molecule or carbon monoxide molecule, then we fail to explain the bond order 3, and if we try to explain the bond order 3, we fail to explain the non-polar nature of this molecule if we use the valence bond approach or valence bond theoretical approach. Now let us see how our molecular orbital theory can explain both of these properties simultaneously. Consider the Coulson treatment for this CO molecule formation. According to this treatment, carbon and oxygen have these electronic configurations. Now before actually mixing of the orbitals, there is a hybridization concept. The hybridization in CO molecule will definitely sp hybridization because it is the only hybridization which leads to the linear geometry, and CO is a linear molecule, and since sp hybridization is a linear hybridization, carbon as well as oxygen, they undergo sp hybridization. This leads to formation of two sp hybrid orbitals in both carbon as well as oxygen. So we can write the electronic configuration of carbon as well as oxygen in the hybridized state as 1s2, sp of carbon 2 and sp of carbon 1, and 2py0 and 2pz1. So this type of electronic configuration we can write. Similarly, oxygen with atomic number 8, we will have 1s2, sp of oxygen 2 electrons and sp of oxygen with 1 electron with 2py2 and 2pz1. So if we write this electronic configuration like this, then the hybrid orbitals can undergo mixing now. Now it means that this Coulson treatment is a mixture of the hybridization concept from valence bond theory followed by the molecular orbital approach. Now if these orbitals or these hybrid orbitals undergo mixing to form the molecular orbital energy level diagram can be shown something like this. So these are the atomic orbital of carbon, which is having 2s, 2px, 2py and 2pz. These are the atomic orbitals of oxygen, which are 2s, 2px, 2py and 2pz. And now these hybrid orbitals of carbon and oxygen can be shown like this. Now these hybrid orbitals definitely should have equal energy, but this is an example of unequal hybridization, or you can say non-degenerate type of hybridization. One of the hybrid orbitals among the two has a lower energy because it has more s character, whereas the second has less s character, and so it has got higher energy. So we can call this as sp1 and sp2. This can also be shown as sp1 and sp2. Now if we observe the energies of these hybrid orbitals, we can see that this sp1 of carbon has a comparable energy as that of sp2 of oxygen, the higher energy orbital among the two hybrid orbitals, whereas sp1 of this oxygen has no orbital having a comparable energy in carbon atom. Hence this sp of oxygen or sp1 of oxygen, it remains as non-bonding type of orbital. Similarly, sp2 of carbon has no comparable energy orbital in oxygen, and so it remains as non-bonding, while this sp1 of carbon mixes with sp2 of oxygen and they form sigma bond. Since it is hybrid orbitals, the bonding will be definitely sigma bonding, and it leads to formation of two molecular orbitals, sigma sp and sigma sp star, and these molecular orbitals will have energies as shown over here. Sigma sp will have lower energy, sigma sp star will have higher energy. Now we are left with the 2px and 2py or 2pz and 2py orbitals, which undergo mixing in a sidewise manner, leading to formation of pi y and pi z molecular orbital along with pi y star and pi z star molecular orbital, or you can say pi 2py, pi 2pz, pi 2py star, pi 2pz star. Now all the molecular orbitals are there with the increasing order of energy, so they will be filled like this. So electrons, number of electrons from carbon are 4, number of electrons from oxygen are 6. So there are 10 electrons which will be filled as sp of oxygen will get 2 electrons, sigma sp will get 2 electrons, pi to py and pi to pz will get 2 electrons each, and sigma sp of carbon, which is non-bonding, will also get 2 electrons. So now there is no electron in the anti-bonding molecular orbital. So this is how the electronic configuration of this carbon monoxide molecule can be shown. And the bond order can be calculated as number of electrons in bonding minus number of electrons in anti-bonding divided by 2. So number of electrons in bonding are this sigma sp has 2 electrons and this 6. So 8 electrons are there in there are 2 electrons in sigma sp and pi y and pi z 2 electrons each. So 6 electrons are there in bonding, whereas there is no electron in anti-bonding. So 6 minus 0 divided by 2 will be equal to 3. So bond order is coming out to be 3. At the same time, we can see that there is a symmetrical distribution of electrons among carbon and oxygen, because we can see that this sp of oxygen is more localized on oxygen, while this sp of carbon is more localized on carbon, and hence there is almost symmetrical distribution of the electrons, leading to non-polarity of the molecule. Hence this molecule can be very well explained by our molecular orbital theory. At the same time, we can explain the bond order as well as bond polarity. If we try to show this molecule, the molecular orbitals, we can see that this is sp of carbon, which is diffused, while sp of oxygen is more centralized on oxygen. This is because this sp of oxygen is having more s character, whereas this sp of carbon is having less s character, and hence it is diffused. This is having more s character, so it will be more centralized on oxygen. As a result, this carbonyl molecule or carbon monoxide molecule has negligible tendency to donate from this side, but has a very strong tendency to donate this lone pair of electrons, because it is diffused and much away from the carbon atom. Hence, this can act as a sigma donor from the sp of carbon or carbon end, while at the same time we have pi star anti-bonding molecular orbital which is empty, and so it can accept electrons in this pi star anti-bonding, thereby it can act as a pi acceptor. This is an interesting case, and which can explain the various metal carbonyl molecules where there is a bonding between metal and carbonyl. At the same time, we are having a sigma bonding between sp orbital of carbonyl molecule, which is a field orbital, and along with that it is overlapping on the empty hybrid orbital of metal, thereby donating the electron pairs to the metal, whereas at the same time the field d orbital of metal overlaps with the empty anti-bonding orbital of carbonyl molecule, and it accepts the electrons from the metal. So this is what is called as the back bonding, and this leads to multiple bond character to the metal carbonyl bond, and this leads to very strong metal carbonyl bonding. So this is how our carbonyl molecule can be very well be explained on the basis of our molecular orbital theory. These two orbitals we can correlate with the molecular orbital energy level diagram, as we have seen previously. This is the molecular energy diagram or molecular orbital energy level diagram of CO molecule. Now there are two orbitals which are involved in bonding. One orbital is the field sp orbital of carbon, and second is the empty anti-bonding molecular orbital. Now if we see this, we can correlate this. The field sp hybrid orbital of carbon is this orbital which is having highest energy among all the field orbitals. So it is called as highest occupied molecular orbital or HOMO, which electron pair is easily donated to the metal because it is having highest energy among all the field orbitals. At the same time, we are having pi star anti-bonding molecular orbital which is empty, and this can be correlated with this pi y star and pi z star, which are the lowest unoccupied molecular orbitals among all, and so these are ready to accept the electron pairs donated by the field d orbitals of the metal. Similar structure can be obtained for the NO molecule. Now in case of NO molecule, we can apply similar treatment as that of carbonyl molecule. The electronic configuration of nitrogen and oxygen similar to carbon and oxygen with one extra electron, and they undergo sp hybridization each, leading to formation of sp of nitrogen and sp of oxygen. There are two sp hybrid orbitals in nitrogen and two sp hybrid orbitals in oxygen, and similar type of molecular orbital diagram can be shown in case of NO molecule also. Only difference is that there is an extra electron in pi star anti-bonding molecular orbital, and so the bond order reduces by a factor of 0.5 because number of electrons in bonding are 6, number of electrons in anti-bonding is 1, and so the bond order is coming out to be 2.5. But if we remove this electron from NO molecule, we get NO positive ion, and NO positive ion is isoelectronic with carbon monoxide molecule, and its bond order will be 3. Coming to a multiple type of bonding like CO2 molecule, it is a triatomic molecule where we have 2 oxygen atoms and 1 carbon atom. So electronic configuration of carbon and oxygen can be shown like this. Now we can have a multiple type of bonding with 2 oxygen atoms with 2 s orbitals, 2 px orbitals, 2 py orbitals and 2 pz orbitals overlapping with the carbon orbitals of 2s, 2px, 2py, 2pz, leading to formation of molecular orbitals which will be filled with total number of electrons equal to 4 electrons in carbon and 6 plus 6 12 electrons in oxygen, leading to filling of 14 electrons in a sequential manner like this. This is all about our molecular orbital aspect. Now let us discuss another theory called as valence shell electron pair repulsion theory. This was put forward by Gillespie and Nilholm in 1957. Now this is relatively new theory as compared to the valence bond as well as the molecular orbital approach. This theory is based on certain rules and is a logical approach or qualitative type of approach towards the repulsion between the orbitals which are present in the molecules. Let us try to understand these rules one by one. The first rule says that the shape of a molecule is determined by number of electron pairs in the valence shell of central atom. The valence shell electrons pairs, they align themselves in such a manner that they are at maximum distance from each other. It is quite obvious that the central atom and bonded atoms, they have their valence shell electron pairs, and the central atom will try to keep the valence shell electron pairs as much away from each other as possible because there is a repulsive force between the valence shell electron pairs, and hence they will remain as much away as possible in the central atom. Because of this particular type of repulsive interaction, if the number of valence shell electron pairs are 2, then they will try to remain away from each other and maximum distance between them will be 180 degrees, leading to a linear geometry. If the number of valence shell electron pairs are 3, the maximum angle between them can be 120 degrees and the geometry will be trigonal planar. If the valence shell electron pairs are 4, the maximum angle between them will be 109.5 degree and it will have a tetrahedral geometry. If the number of valence shell electron pairs are 5, the structure will be trigonal bipyramidal with the bond angles at 120 degree and 90 degree. If there are 6 valence shell electron pairs, the geometry will be octahedral with all the orbitals aligned at 90 degrees with respect to each other. And if the number of valence shell electron pairs are 7, then the geometry will be pentagonal bipyramidal with the angles of 72 degree and 90 degree. We will try to understand this with examples of certain molecules. Suppose we have a molecule like BeF2. Now beryllium has 2 electrons in the valence shell and each fluorine is contributing 1 electron from itself. So there are 4 electrons on the central beryllium atom in its valence shell, 2 of its own and 2 donated or 2 coordinated with the fluorine atoms. As a result, what we have are 2 valence shell electron pairs, and these pairs will try to remain as much away as possible from each other due to repulsive interaction, and the maximum distance between them can be at 180 degrees, and so the angle between these 2 valence shell electron pairs will be 180 degrees, with the geometry will be linear. When we come to another molecule like BF3, now boron has 3 electrons in the valence shell and each fluorine has 1 electron. So there are 6 electrons in the valence shell of boron. That is, there are 3 valence shell electron pairs and the maximum angle between them will be 120 degrees. So the geometry will be trigonal planar. Coming to CH4 molecule, carbon has 4 electrons in the valence shell. Each hydrogen is contributing 1 electron. As a result, there are 8 electrons, meaning that there are 4 valence shell electron pairs. Hence, they try to remain as much away from each other as possible, and so the angle will be 109.5 degrees with a geometry of tetrahedral. In case of PCl5, valence shell of phosphorus contains 5 electrons and each chlorine contributing 1 electron, meaning that there are 10 electrons or 5 valence shell electron pairs, and so the geometry will be trigonal bipyramidal and the bond angles will be 120 degree and 90 degree. In case of SF6, the valence shell of sulfur has 6 electrons while each fluorine is contributing 1 electron. So overall 12 electrons are there, that is 6 valence shell electron pairs which try to remain away from each other at 90 degree, and as a result the geometry of the molecule will be octahedral. Coming to IF7 molecule, iodine has 7 electrons of its own in its valence shell and each fluorine is contributing 1 electron. So there are 14 electrons, and meaning that there are 7 valence shell electron pairs, and so the geometry will be pentagonal bipyramidal. Now we can see we have discussed valence bond theory and now the VSEPR theory. Now, valence bond theory can also explain all these properties only after considering the concept of hybridization. But valence shell electron pair repulsion theory without considering the hybridization can explain geometries of all these molecules purely on the basis of interelectronic repulsions between the valence shell electron pairs. Second rule of VSEPR theory says that lone pair of electron occupies more space on the central atom, and so the repulsion between lone pairs is more. Thus, if a molecule contains lone pair of electron, the geometry gets distorted. Quite obvious if we consider a molecule like AB. The electron pair in this particular molecule will be located in between the 2 atoms A and B. And so the space occupied by the electron pair on a particular molecule is less, or particular atom is less. So this electron cloud is distributed between the 2 atoms. But if it is a lone pair, it is a property of a particular atom, and so such lone pair will occupy more space on that particular atom. So this is a quite logical approach towards the bonding concept or the electron pair concept. Now the outcome of this is that if you have lone pairs, then the repulsion between the lone pairs will be maximum because they are occupying more space on the central atom, whereas the repulsion between bond pairs is minimum because they are occupying less space on the central atom and the electron cloud is diffused. Hence, we can say that the repulsion between lone pair is maximum, while the repulsion between 2 bond pairs is minimum, while the repulsion between a lone pair and a bond pair will be intermediate between the 2. An important outcome of this we can see through an example. If we consider a molecule like CH4, now in case of CH4, carbon atom has 4 electrons in the valence shell, each hydrogen is contributing 1 electron. So there are 8 electrons, that is 4 valence shell electron pairs. And all of them are in the form of bond pairs because there are 4 bonds. So 8 electrons, that is 4 valence shell electron pairs forming 4 bonds. So there is no lone pair, and hence the repulsion between all of them is equal. As a result, the structure is symmetrical with all the bond angles of 109.5 degree. When we come to another molecule like NH3, now in case of NH3, there is 1 lone pair and 3 bond pairs. Now because of this lone pair, which occupies more space on the central atom, it exerts more repulsive forces on the bond pairs. As a result, the angle between bond pair decreases from 109.5 degrees, which is a standard bond angle in case of tetrahedral geometry. It reduces to 107 degree in NH3 molecule. If we extend this concept further to another molecule like H2O, we can see that there are 2 lone pairs. Now the repulsion between 2 lone pairs is maximum according to this rule, and hence since there is a lot of repulsion between these two, they will push the bond pairs away from themselves. As a result, the angle between the bond pairs further reduces, and hence the bond angle in case of H2O molecule is just 104.5 degrees. So in general, we can say that if there is no lone pair, the geometry is regular and the bond angles match with the standard bond angles which are given in rule number 1. But if there are lone pairs, 1 or more lone pairs, definitely the geometry gets distorted and also the bond angle gets altered from the natural bond angles. In case of NH3, there is 1 lone pair. In case of H2O, there are 2 lone pairs. So more is the number of lone pairs, less will be the bond angle, because the separation between the bond pairs will go on decreasing due to lone pair repulsion. Coming to third rule, it says that greater is the electronegativity of the central atom, it pulls the bond pair of electron towards itself and thus increases the repulsion between them. Hence, the bond angle increases. Let us try to understand this concept taking an example. For example, if you have a molecule like H2S. Now, in case of H2S, there are 2 lone pairs and 2 bond pairs. Now, because of these 2 lone pairs, definitely there will be more repulsive forces acting between them, and also the repulsion between lone pair and bond pair will be more. Hence, the bond angle reduces to 92.1 degree. But if we compare this with the H2O molecule, we can see that in case of H2O, oxygen is more electronegative as compared to sulfur in H2S. Hence, these bond pairs of electrons are attracted more towards oxygen. Now, since they are attracted more towards oxygen, there will be more repulsion between them because the distance between them is decreasing now. Hence, due to larger repulsion between them, the bond angle increases to 104.5 degree. So if we compare these two, the bonded atoms are same, but the central atoms are different with different electronegativities. More is the electronegativity of the central atom, more closer will be the bond pairs towards it, and more will be repulsion between them, leading to larger bond angles. Now, similarly, if the electronegativity of the bonded atom is more, the electron pairs are pulled away from the central atom, thereby decreasing the repulsion. Now consider an example of OF2 molecule or F2O molecule. Now in this case, we have central atom as common as that of H2O, but the bonded atom has changed. Now we have substituted hydrogen with fluorine. Now in case of fluorine, we know that fluorine is more electronegative than oxygen. So it pulls the electron pair towards itself. As a result, the distance between these electron pairs or bond pairs decreases. Hence, the repulsive interaction decreases and they can come closer, and the bond angle reduces from 104.5 to 103.1 degree. Next rule says that multiple bond does not alter the geometry of the molecule. It only increases the bond angle due to higher electron charge density. Let us take an example of a molecule like POCl3. Now in case of POCl3, the phosphorus atom has 4 valence shell electron pairs around it, as if we consider only the sigma bonds, and we do not consider the pi bond. It does not affect the overall geometry of the molecule. The geometry remains same as tetrahedral, but since it is a double bond, there are 4 electrons, which will lead to more repulsive forces between this bond and this bond. So bond pair repulsion will be more in this case, and as a result the angle between these bonds will definitely decrease, while the angle between these bonds will definitely increase. So the bond angle decreases from a natural bond angle of 109.5 degree in tetrahedral geometry to 103 degree in case of POCl3 molecule. Rule number 5 says that if the valence shell of a central atom is completely filled, the repulsion is more, while if it is incomplete, the repulsion is less. This can also be explained on the basis of the same example which we have seen previously. If we consider H2O and H2S molecules, now oxygen has a valence shell which is a second shell, while sulfur has a valence shell which is a third shell. Now if we consider this molecule, the valence shell of oxygen is second shell having a capacity of 8 electrons, and it is already getting 8 electrons, the 2 bond pairs from hydrogen and 2 lone pairs of its own. So there are 8 electrons in the valence shell of oxygen, and hence the repulsive interaction between them will be more and bond angle will be more. But in case of sulfur, the valence shell is the third shell, which is having a capacity of 18 electrons, and as a result, as it has having only 8 electrons in the valence shell, the repulsion between them will be less, and hence the bond angle will reduce to 92.1 degree. So this reduction in the bond angle from H2O to H2S can be explained on 2 different bases. One, the electronegativity difference, and the completely filled and incomplete valence shells of the sulfur atom. Next rule says that repulsion is maximum when the electron pairs are at 90 degree, while it decreases sharply with increase in bond angle and become minimum at 180 degree. An important outcome of this is the geometry, which is trigonal bipyramidal geometry. Now if we consider the trigonal bipyramidal geometry, we have got different angles. All the bonds are not equivalent. There are 3 equatorial bonds and 2 axial bonds. Now if there is a lone pair and lone pair occupies the axial position like this, then there will be 3 repulsive interactions at 90 degrees. But if the lone pair occupies equatorial type of position, then there will be only 2 repulsions at 90 degrees. Hence there will be less repulsion in this case, leading to more stability, and hence we can say that the lone pair in case of trigonal bipyramidal geometry will definitely occupy the equatorial position. This is an important outcome of this rule, that the lone pair will occupy equatorial position in case of trigonal bipyramidal geometry. The same will be the case in case of various molecules we will see in our next discussion. Now we can apply the valence shell electron pair repulsion theory by calculating the number of valence shell electron pairs around the central atom. The number of valence shell electron pairs can be calculated as half of V plus M plus A minus C. We will see what is this. V is equal to number of valence shell electrons in the central atom. M is the number of monovalent substituents present on that atom. A is the charge on anion if it is an anionic species, and C is the charge on cation if it is a cationic species. Obviously, number of valence shell electron pairs will be equal to half of number of valence shell electrons. Now these electrons are coming from various contributions: the number of valence shell electrons of the atom itself, number of electrons which are contributed by the substituents, number of electrons which are obtained due to negative charge, minus number of electrons which are lost due to the positive charge. We will use this particular equation and we will explain the shapes of various molecules according to valence shell electron pair repulsion theory. Consider the application of VSEPR theory to NH3 molecule. Now in case of NH3 molecule, the number of valence shell electron pairs can be calculated as half V plus M plus A minus C. Now this is half V is the valence shell electrons in nitrogen atom, which is equal to 5, plus number of monovalent substituents. So all the three hydrogen atoms are monovalent. So 5 plus 3, there is no charge on it. So A and C will become 0. So this will be half of 8 will be equal to 4. And since valence shell electron pairs are 4, the geometry has to be tetrahedral according to rule number 1 of valence shell electron pair repulsion theory. But since out of the 4, there are only 3 bond pairs, because only 3 bonds are formed with 3 hydrogen atoms. Since there are only 3 hydrogen atoms, bond pairs are 3. So out of the 4, 3 are bond pairs, indicating that one must be a lone pair. And in case of 4 valence shell electron pair, the geometry has to be tetrahedral with 1 lone pair and 3 bond pairs like this. Because of the lone pair, according to rule number 2, we know that lone pair exerts more repulsive force. As a result, the bond angle decreases from a standard bond angle of 109.5 degree to 107 degree. As a result, the geometry has been changed from tetrahedral to trigonal pyramidal, and bond angle has also decreased because of the lone pair which is present on nitrogen atom. Coming to H2O molecule. Now valence shell electron pairs on central oxygen atom can be calculated as half V plus M plus A minus C, which is equal to half into number of electrons in the valence shell of oxygen are 6 plus number of monovalent substituents, that is hydrogen, it is equal to 2. So half of this will be equal to 4, indicating that the geometry should be tetrahedral according to rule number 1. But since there are only 2 hydrogen atoms, it means that the bond pairs are only 2, and hence there should be 2 lone pairs, 2 bond pairs, 2 lone pairs, overall geometry tetrahedral. But because of the 2 lone pairs, definitely the geometry has been changed to V-shaped or bent molecule, and the bond angle further reduces to 104.5 degree from the natural bond angle of 109.5 degree due to 2 lone pairs on oxygen atom. Consider a molecular ion like NH4 positive ion. Now it is an interesting part of VSEPR theory that we can not only explain the geometries of the molecules, but we can explain the geometries of various ions also. So let us see NH4 positive ion. Without considering any concept like hybridization, we can explain its geometry purely on the basis of repulsion between the valence shell electron pairs. Let us discuss this. So number of valence shell electron pairs on the central atom, which is nitrogen atom, is equal to half V plus M plus A minus C. So equal to half into number of electrons in the valence shell of nitrogen are 5 plus number of monovalent substituents, which is hydrogen, that is equal to 4, plus 0, there is no anionic charge, but there is a cationic charge, that is positive charge. So the number of valence shell electron pairs are coming out to be 4, indicating that the geometry should be tetrahedral. But we can see that all the 4 geometry or 4 electron pairs are in the form of bond pairs, because there are 4 hydrogen atoms which are forming the bond. Hence there is no lone pair at all. Because of no lone pair, the geometry will be a standard geometry or a regular geometry of tetrahedral structure, and the bond angle will be exactly 109.5 degrees as expected. So structure is tetrahedral with a regular tetrahedral geometry and a standard bond angle of natural value, that is 109.5 degree. Coming to another interesting molecule, which is ClF3 molecule, chlorine trifluoride. Now in this molecule, the central atom is chlorine. So number of valence shell electron pairs in chlorine can be calculated as half into number of electrons in the valence shell of chlorine equal to 7 plus three monovalent substituents in the form of fluorine atoms, there is no cationic or anionic charge. So number of valence shell electron pairs are coming out to be equal to 5. And 5 valence shell electron pairs, meaning that the geometry should be trigonal bipyramidal as per the rule number 1 of our VSEPR theory. Now, out of these 5 valence shell electron pairs, there will be 3 bond pairs because only 3 bonds are formed with fluorine, while remaining 2 will be lone pairs. And we know that in case of trigonal bipyramidal geometry, the lone pairs definitely occupy equatorial position because the repulsive interaction is minimum if the lone pairs occupy equatorial position. And hence the structure will be something like this, with trigonal bipyramidal geometry with 2 lone pairs occupying the equatorial position, while the axial bonds are formed by 2 fluorine atoms and 1 equatorial bond by 1 fluorine atom. Hence the geometry will be trigonal bipyramidal, but due to lone pair it shifts to T-shaped type of geometry. This is a T shape with 3 fluorine atoms are at 90 degrees theoretically, but because of these lone pairs exerting a repulsive interaction, the bond angle between FClF reduces to 87.5 degree. So this 87.5 degree is reduction from the natural bond angle of 90 degree. So it is actually a T-shaped molecule with slightly lesser or distorted type of geometry with a lesser bond angle. Another interesting molecule is SF4 molecule. Now in SF4 molecule, the number of valence shell electron pairs will be equal to half into number of electrons in the valence shell of sulfur atom are 6 plus 4 monovalent substituents and no charges. So the number of valence shell electron pairs are coming out to be 5, indicating that the geometry should be trigonal bipyramidal according to rule number 1. But out of the 5, only 4 are bond pairs because only 4 fluorine atoms are forming the bond, indicating that one is to be definitely the lone pair. Now in case of trigonal bipyramidal geometry, the lone pair occupies equatorial position so as to have minimum repulsion, and so the geometry will be something like this: one lone pair occupying the equatorial position, while 2 fluorine atoms in the equatorial position and 2 fluorine atoms at axial position. And hence, even if the expected geometry is trigonal bipyramidal, because of one lone pair occupying the equatorial position, the geometry becomes a seesaw shaped. Now this seesaw shape can be shown something like this. So we can see that this sulfur atom is present at the center. This is acting as a base of the seesaw, and these are the two opposite sides of the seesaw. Now since there is a lone pair on this side which will exert more repulsive forces, the bond angle between this fluorine and this fluorine, which is expected to be exactly 90 degrees, becomes slightly less than 90 degree, and it gets deviated from its natural bond angle. Another interesting molecule is I3 negative ion. This is triiodide ion, and we see that this type of ion is possible or is formed when we mix Ki with iodine molecule to give Ki3 type of salts. So this I3 negative ion has got one iodine at the center, while 2 iodine are in the form of bonded atoms. So central atom is iodine, which is having 7 electrons in the valence shell, and 2 monovalent iodines bonded with it. So 7 plus 2, plus there is an anionic charge, so 1 electron from the charge, indicating that there are 5 valence shell electron pairs, showing the geometry should be trigonal bipyramidal. But since there are only 2 iodine atoms bonded to the central iodine atom, the bond pairs are only 2, indicating that there are 3 lone pairs, and lone pairs occupy equatorial position. Thereby the geometry can be shown something like this. So this is iodine, which is central iodine, and these 2 iodine atoms are bonded iodine, and these 3 lone pairs are present at equatorial positions. Since all the three iodine atoms are in a straight line at exactly 180 degrees, the geometry is linear. So we can see that this theory can very well explain the geometries of various ions also, cations as well as anions. This is a structure which is a linear structure, one iodine atom at the center and two iodine atoms at in a linear fashion bonded with the central one. Next molecule is BrF5. Now the central atom is bromine with number of valence shell electrons as 7, 5 monovalent fluorine substituents. So 7 plus 5 divided by 2 will be equal to 6. Now since there are 6 valence shell electron pair, the expected geometry is octahedral. But out of the 6, there are only 5 bonds are formed, indicating that bond pairs are 5, means one remaining should be a lone pair. And in case of octahedral geometry, all the positions are equivalent at 90 degrees, and so lone pair can go to any of these positions. Suppose this lone pair is shown at this particular point, we can see that the geometry will have 5 fluorine atoms, 4 in a plane and 1 below the plane or above the plane, we can say. The bond angle, which is expected to be 90 degrees, has been reduced to 85.1 degree because of the repulsive interaction with this lone pair of electrons. And so the geometry becomes square pyramidal as shown over here. This becomes a square pyramidal, but not exactly a regular square pyramidal, which is normally expected bond angles are 90 degrees, but now the bond angles have been reduced to 85.1 degree due to the lone pair present on the bromine atom. One more ionic species, that is ICl4 negative ion. So this is type of a polyhalide type of ion. Iodine is the central atom. So number of valence shell electron pairs can be calculated as 7 electrons in the valence shell of iodine plus 4 monovalent chlorine substituents plus 1 electron because of the negative charge, which is equal to 6. Expected geometry is octahedral, but out of the 6 there are only 4 bond pairs, indicating that 2 should be lone pairs, and these lone pairs in octahedral geometry will definitely be at maximum distance from each other, so they will acquire or they will adopt the opposite positions, that is what we call it as a transpositions with respect to each other, and the 4 bond pairs will remain in the plane while the 2 lone pairs will be maximum away from each other at 180 degrees in order to decrease the repulsive forces. And so even if the expected geometry is octahedral, but 2 lone pairs occupying the opposite positions, making the geometry as square planar in case of ICl4 molecule. This is the shape of ICl4 molecule, can be seen as a square planar type of molecule with all the Cl-ICl bond angles as 90 degrees. This is another most common ion in the inorganic molecules called as the sulfate ions, that is SO4 with 2 negative charges. So it is an anionic species, but in this case we can see that all the 4 substituents are divalent, so there is no monovalent substituent. So we can calculate the number of valence shell electron pairs as half into number of electrons in the valence shell of sulfur are 6 plus 0 monovalent substituents and plus 2 negative charges. So total number of electrons associated with sulfur will be 8, that is equal to number of valence shell electron pairs as 4, leading to tetrahedral geometry. And among this we can see that all the 4 valencies are satisfied by the oxygen atoms. So all the 4 are bond pairs and there is no lone pair, and hence the geometry should be perfectly tetrahedral. We can see that there are 2 double bonded oxygen atoms and 2 single bonded oxide ions. Now this is a structure which undergoes resonance, and because of resonance all the bond angles are equivalent with 109.5 degrees and the geometry is perfectly tetrahedral in nature. Another important molecule is carbon CO3 2 negative, that is what we call it as a carbonate ion. Now this carbonate ion has central carbon atom with 4 valence shell electrons and 2 negative charges from the 2 minus anionic charge. So total there are 3 valence shell electron pairs leading to trigonal planar geometry. In trigonal planar geometry, all the 3 are bond pairs because 3 oxygen atoms are there, and because of this the geometry will be trigonal planar. Similar to sulfate ion, there will be resonance of these double bonds, and because of the resonance all the bond angles are 120 degrees and the geometry is perfectly trigonal planar. One more example we can consider is the 3 species which are formed by NO2, that is NO2 molecule, NO2 positive ion and NO2 negative ion. Now in case of NO2 molecule, the number of valence shell electron pairs can be calculated as half into 5 electrons in the valence shell of nitrogen. There are no monovalent substituents. There is no charge on cation or anion. So you can see that the number of valence shell electron pairs are 2.5. That is 5 electrons leading to 2.5 valence shell electron pairs. Now out of these, 2 are bonded with oxygen, so 2 bond pairs are there, and lone pair will be 0.5, that is a single electron, and so this leads to a V-shaped structure of the molecule with a single electron in one of the orbitals on nitrogen. It is localized on nitrogen. Similarly, when we come to NO2 positive, now that electron is lost and hence the number of valence shell electron pairs become 2, and because of this the structure becomes linear and the bond pairs are 2, there is no lone pair, and the molecule becomes NO2 with a positive charge, and it is a linear molecule similar to carbon dioxide, and we can see that it is isoelectronic with carbon dioxide molecule. An important outcome of VSEPR theory is that isoelectronic molecules are isostructural too. Coming to the NO2 negative ion. Now there is one additional electron added to that. As a result, the structure will have 3 valence shell electron pairs leading to trigonal planar geometry, and out of that there will be 2 bond pairs and 1 lone pair on nitrogen leading to trigonal planar geometry changing to V shape because of 1 lone pair on nitrogen. Now if we see these 3 structures, there is no lone pair on nitrogen, there is a single unpaired electron on this nitrogen, and there is 1 lone pair on this nitrogen. Now we can see that this as well as this species, the positively charged species as well as the negatively charged species, are diamagnetic in nature because of no unpaired electron, while the molecular NO2 is paramagnetic in nature due to unpaired electron.